Somewhere in the dark, between stars, there is an object cold enough to have clouds of actual water vapor drifting through its atmosphere. It has almost no light of its own. It formed exactly like a star, collapsing out of gas and dust under its own gravity, and then something inside it simply refused to ignite. That failure has a name. Brown dwarfs are not stars, and they are not planets. They are something caught in between, massive enough to almost become suns, and small enough to spend eternity failing. There are several distinct kinds of these almost stars scattered across the galaxy, and the differences between them are the difference between a faint red ember and something so cold you could theoretically stand near it in a snowsuit. But the coldest one on record is stranger than anything on this list so far, and it barely counts as warm at all. Y-dwarfs are the coldest class of brown dwarf ever confirmed to exist. Their surface temperatures can drop close to room temperature, somewhere near 25 degrees Celsius. Cooler than the surface of Venus, cooler than a summer day on Earth. Take an object with the mass of dozens of Jupiters and cool it down until it stops glowing in visible light entirely, and you get a Y-dwarf, a failed star radiating almost nothing but heat in the infrared. One of the closest known examples sits roughly 7 light-years from Earth, discovered in 2014, drifting in silence with no planets, no light show, no reason for anything to notice it was there. But go slightly warmer, and the atmosphere itself starts to change into something far more violent. T-dwarfs burn only slightly hotter, typically between 500 and 1300 Kelvin, and their atmospheres are thick with methane, the same gas found in the clouds of Jupiter and Neptune. Their spectra show deep, unmistakable methane absorption bands, a chemical signature stars can never produce because stars are simply too hot for methane to survive. Picture a world lit by nothing, its own gravity keeping a faint core glow alive, while methane clouds churn overhead in permanent darkness. The first T-dwarf ever confirmed was identified in 1995, orbiting a nearby star, and it rewrote what astronomers thought a failed star could even look like. But methane dwarfs are calm compared to what comes next, because the next class does not just have clouds, it has weather violent enough to reshape its entire face. L-dwarfs run hotter still, often between 1300 and 2000 Kelvin, hot enough that clouds of vaporized minerals and silicate dust form high in their atmospheres, the same materials that make up rock here on Earth. Storms on some L-dwarfs have been tracked, rotating across their surfaces. Dust clouds the size of entire planets, moving in bands like a hurricane that never ends. Take a superheated ember with a stormy sky made of rock vapor instead of water, and you get an L-dwarf glowing a deep, dim red that would be nearly invisible from more than a few light years away. If you've made it this far into the failed stars scattered across our galaxy, drop a like right now, because the next category is not about temperature at all. It is about something far stranger, an object with no star to call its own. Rogue brown dwarfs drift completely alone, untethered from any solar system, never having formed a planet, a companion, or a home. Unlike stars, which almost always form in clusters and often keep gravitational partners for billions of years, a rogue brown dwarf can be ejected during formation and simply fall into the silence between stars forever. One of the closest known examples, WISE 0855, sits just over 7 light-years away and is colder than nearly anything else discovered outside our own solar system. No sunrise, no orbit, no light source, but itself. It travels through the galaxy completely in the dark, and there is no way to know how many more are drifting nearby, undetected. simply because they emit almost nothing bright enough to see. But not every brown dwarf ends up alone. Some of them found a partner in failure. Binary brown dwarfs form when two of these failed stars end up gravitationally bound to each other, orbiting a shared center of mass instead of drifting solo. One of the closest and most studied pairs, discovered in 2013, sits roughly 6.5 light-years from Earth, and consists of two brown dwarfs locked in a tight, fast orbit around one another. Astronomers have used this system to map out weather patterns in real time, watching storm bands rotate across the surface as the two objects circle each other in near total darkness. Two failed suns, bound together forever, neither one ever bright enough to illuminate the other. And here is where things get strange, because being a brown dwarf is not actually about mass alone. It is about a threshold, a specific number of Jupiters, that decides whether an object burns anything at all. Lithium-burning brown dwarfs sit at a very specific point on the mass scale, somewhere around 65 times the mass of Jupiter, just heavy enough to briefly fuse lithium in their cores before that fuel runs out entirely. This process lasts a tiny fraction of the object's life, and once the lithium is gone, the core goes cold, and stays that way for the rest of its existence, sometimes for tens of billions of years. Astronomers actually use the presence or absence of lithium as a direct test, called the lithium test, to determine whether a faint object is a true brown dwarf or a very small, very dim star. A brief flicker of fusion, then silence for the rest of time. But lithium burning is barely fusion at all. The next threshold up involves an element that actually defines what a brown dwarf is. Deuterium-burning brown dwarfs are the ones that meet the technical definition most astronomers actually use. Objects with roughly 13 to 80 times the mass of Jupiter, heavy enough to fuse deuterium, a heavier form of hydrogen, but never heavy enough to sustain full hydrogen fusion the way real stars do. This deuterium burning can last for millions of years, longer than lithium fusion, generating just enough heat to keep the object glowing dimly in infrared long after formation. Take a ball of gas 13 times heavier than Jupiter. Let gravity crush its core just enough to spark deuterium fusion, and you get the textbook brown dwarf, a true failed star according to the official mass boundary. But cross that boundary going the other direction, and the object stops being a brown dwarf entirely and becomes something even more ambiguous. Sub-brown dwarfs fall below the deuterium-burning threshold under roughly 13 Jupiter masses, meaning they never ignite any kind of fusion at all, not even briefly. The unsettling part is that some of these objects appear to have formed the exact same way stars do, collapsing directly out of a cloud of gas rather than growing slowly inside a disk of planetary debris. That means an object with no fusion whatsoever might still, by formation history, be closer to a failed star than to a real planet. And there is currently no perfect way to sort every one of them into a clean category. We have observed several candidates like this floating freely through nearby star-forming regions, and astronomers still argue over what to even call them, and that uncertainty becomes almost unbearable with the very last category on this list, the one sitting right at the edge of actual stardom. The most massive brown dwarfs, hovering just under 80 Jupiter masses, are the closest any object can get to becoming a real star without ever crossing the line. At that mass, the core comes within a fraction of the pressure and temperature required to sustain full hydrogen fusion, the process that powers every star in the sky. Push just slightly past that threshold, and gravity would finally win. Hydrogen fusion would ignite, and the object would begin shining as a true star for billions of years. Instead, it sits forever just beneath that ignition point, radiating away the heat of its own formation, slowly fading. A star in almost every way except the one that matters most. No sustained fusion. No true light. Just a long, dim collapse into darkness that can last longer than the current age of the universe itself. That is, every known category of failed star currently understood by astronomers, from objects barely warmer than a room to giants that missed becoming a sun by the smallest possible margin. Somewhere out there, in the dark spaces between the stars you can actually see, more of these failed suns are almost certainly drifting right now, cold, unlit, and completely undetected. If this kind of scale makes the universe feel a little bigger and a little colder, subscribe before the next failed star drifts past unnoticed. And if you are not ready to leave the dark places yet, there is a full playlist waiting exactly where this one leaves off.